Hi there! In this video we will go over the Criterion C reflections, those short reflections you did at the end of every lesson in the transformations unit. This should be helpful when preparing for our unit assessment, so let's get rolling. Okay, the first thing we did way back when was this one. It says, explain what effect negative g of x will have on the graph of g of x. So here's the function g of x. It's x squared, and we can see it in red here. What effect will applying a negative sign to that function have? Well, putting a negative sign in front of a function is like saying you're turning all the y values negative. You're affecting the y values. Therefore, if we're changing y values from positive to negative, we are reflecting it over the x-axis. Okay, so the effect it will have is this. It will reflect it over the x-axis, changing it into a concave down parabola with the same vertex. So this one, the red parabola, all its values, y values, will be made negative, so it'll end up being down here. It has been reflected over the x-axis. Alright, next, explain what effect f of negative x will have on the graph of f of x. So here's the function f of x. That is this blue parabola right here. And now we are doing this transformation, f of negative x. So now instead of making the y values negative like we did here with negative g of x, we're making just the x values negative because we see a negative applied to the x. So therefore, if every x value becomes negative, imagine this blue parabola, all the x points become negative, they will jump to this side. So we are reflecting it over the y-axis. So it will reflect it over the y-axis. And it says, where will the vertex be? Well, the vertex is here at 2, negative 4, and if we reflect over the y-axis, the vertex will be here at negative 2, negative 4. And you can see this blue dotted line represents that reflection here. Okay, why will g of negative x seemingly have no effect on the graph of g of x? So now we're back to the red parabola. That's g of x. And it's saying if you apply g of negative x, so we just said negative x makes all the x values negative, which means a reflection over the y-axis. So imagine taking this red parabola and reflecting it over the y-axis. Well, it will be like spinning it around this line here. This is the y-axis, right? If a parabola is spinning around this line here and it has its vertex at the center here, there's no effect because this half of the parabola will end up where this half is right now, and this half of the parabola will end up where this half is. So it's just flipping it around, but it will sit on top of its old self. So it says y will seemingly have no effect because it's a reflection of the y-axis. It will not move the parabola, so there will seem to be no effect. However, there is a effect. There is still a reflection. So all these points, like I said here, will end up being over here. For example, the point 2, 4 will reflect across and become the point negative 2, 4. And likewise, the point negative 2, 4 will then be over here. Basically, you're swapping the points. So it looks the same, but the points have been swapped, so it's important to note that. Okay, next question. Discuss the curve's relationship to the asymptote. Okay, so here's a curve. It's an exponential curve, and it has something called an asymptote. The asymptote is, and I'll explain it here. So the asymptote is this dotted line, and the curve will forever approach that dotted line but never reach it. So here's a more mathematical explanation. As we move towards negative infinity along the x-axis, the curve approaches the asymptote, which is at y equals 0, but never reaches it. It looks like it reaches it, but imagine it's always just slightly above y equals 0. And therefore the range is y values such that y values are greater than or equal to 0. Oh, shouldn't be equal to, that should just say greater than 0. So let me change that, that's important. Alright, there we go. So y values are greater than 0 but less than infinity, because the y values that are possible on this curve go all the way up to infinity, but then they never get to 0. So y values are greater than 0, less than infinity. Perfect. What effect does each have on the graph? Which does not move the asymptote? Okay, this one here. Whenever we see numbers added or subtracted to x only, that is a horizontal effect because we're affecting x values. When we see a positive here, we actually move it in the opposite direction. So this is a horizontal translation, left 2 units. So here is how this graph would move. It would move like this. So it moved from here, left 2 units over here. And if that graph moved left to right, the asymptote just remains where it is. The asymptote also moves left to right. It just slides along where it is, so it doesn't change. Now, f of x plus 3. Now we're adding a number to the entire function, so we're adding numbers to y. And that means the entire function goes up. It's a vertical translation, up 3. So whenever we see a number added to the function, we're moving it up or down. So in this case, we move up 3 units. You see the curve ends up here. And now the asymptote does move, because if the whole curve moves up, then the asymptote also travels up with it, and the asymptote is now here at y equals 3. Right, continuing on, where does the given point, this point right here, 1, 3, move to based on each? Here is a 4 in front of the function, so again we're affecting the y values. This is a vertical dilation, and it is a vertical dilation of factor 4. So that means this point here, every y value, because we're affecting y, every y value becomes 4 times what it was. So this coordinate will, the x value will remain 1, but 3 will be multiplied by 4, so the new location will be 1/12 of that point. Okay, over here, we have a horizontal dilation, because now we have the multiplier with the x. But with horizontal dilations, the effect is the opposite of what we see. We see 2, therefore the effect is actually a scale factor of 1/2. Okay, we take a reciprocal. And that means this point, which was once at 1, 3, now the x value becomes half of what it was. So that 1 becomes a half, but the y value remains at 3. All right, let's keep going. Here's another problem we had. It says for each, write g of x in terms of f of x. So we want to write blue function as taken from the red function. So how do we turn the red one into the blue one? And notice here it gives you these 2 points. So you can see that that point, the x value remains the same, but the y value has been doubled. So we have a vertical dilation. So 2 times f of x. Every y value is 2 times what it was. Okay, over here, notice we're given some points. Here's 1, 4, here's 2, 4. So this time the y value remained the same, 4 and 4, but the x value became double what it was. So that's a horizontal dilation. But since we're stretching it and making it 2 times, oh wait, we're writing g of x in terms of f of x. Okay, so g of x is actually half of f of x, right? G of x is the blue one. So the x value is half, therefore inside here we have a 2, right? Because we said if we see the effect as a half on the graph in the function, it's a 2 here. Okay, let's look at this last one here. We're trying to turn f of x into g of x. To do that, we can reflect this red one over the x-axis, so it will become a concave down parabola down here. And currently the vertex is at -3, 2, so if you reflect it, it will be at -3, -2 right here. And then imagine that parabola is sitting there. We have to then move it 1, 2, 3, 4, 5 units over. Is that right? 1, 2, 3, 4, 5. Yeah, 5 units to the right so that it matches this one. So here is the transformation we're going to perform. There's 2 steps in there. Negative f of x means we're reflecting it over the x-axis. And then x minus 5 means we're moving it 5 units right. Next one, we're supposed to describe the transformations for each of these. So we begin with the purple one here, f, and we're trying to turn it into all of these. Let's begin with g. Okay, when we turn f into g, we notice it's basically taking that W shape and making it wider. But how much wider? Well, this corner of f is at x value of -2, and now over here, that corner is at -8. So that means that became 4 times wider. Okay, so g is 4 times wider than f. And if it's 4 times wider, we're going to write it like this. Okay, we're affecting horizontal translation, affecting x values, but we're not going to write 4 here. We write 1/4, because remember, with the x dilations, we do the reciprocal of what we see. The multiplier is 4, therefore we write 1/4 here. Okay, next one, let's look at r. Okay, to get from purple to r, from f to r, we can maybe reflect this over the axis and then move it, right? So let's take a look at what I have here. We're reflecting it over the x-axis, putting the negative in front of the function. That will flip this one over and make it an M shape. And then we have to move it. So let's take, for example, this point here. When we reflect it, that point ends up being here. Then we have to move it 1, 2, 3, 4 units left, and 1, 2, 3, 4, 5 units up. And that's what we see here. 4 units left is +4, and 5 units up right here. Okay, how about getting the S one here? So this one certainly looks like it's going to be stretched to become this one. It's going to be stretched vertically. And how tall is this one right now? It goes from 2 down to -2. So this thing has a height of 4 currently. And this one, the big green one, has a height of 8. So we need to stretch this, basically double it. So we double it in height. And if we double it in height, this point goes down to -4. So then imagine how you have to move it. You have to move it up 4 units, and over 5 units. Let's check what we have here. Here it is. There's the double for the vertical dilation. Makes this thing twice as high, makes it 8 units tall. And then there's the movement. 5 units to the right and 4 units up. A lot of students get this 4 wrong because they think that even after the stretch, this point remains right here. And then they just move it up 2 units. But remember, when we're stretching here, that -2 will become -4, and that +2 will become +4. So that's how we have to remember to do it. Okay, let's take a look at this one. We're trying to write g of x in terms of f of x. So this function in terms of this function. Okay, so begin with this one, and we're going to move it over 1, 2, 3, 4, 5 units. And then we want to flip it or reflect it over the x-axis. So let's see how that's done. We're going to take the f of x one, reflect it, there's the reflection, and then 5 units to the right. Okay, so flip that over, and then move it over 5 units. Okay, given that f of x has this equation, so this parabola here has this equation, write g of x in terms of f of x. So this function here, we often do transformations like this. We begin like this, where we say, what is g of x in terms of f of x? But now we want to write just g of x in terms of x. We don't want this f in here anymore. We want to write just what is the g of x function. So we're going to apply these 2 changes to this function here. Check out how we do that. So we know already that to get g of x, we apply a negative to the function f. So here's the negative put in front of this whole function. Okay, so that negative is put here. Notice this -1 became a +1 because that negative is applied to the entire function, and that's what I did here. Negative went here, and it also applied here, which became +1. And then we insert x minus 5 into the f function. So right here we have x in the f function. That's going to be replaced by x minus 5 right here. And there it is right there. That simplifies further. X minus 5 plus 3 is -2. There's that negative in front still, and remember that that 1 is now positive. And also notice that let's take a look actually. Let's compare this one to the g of x function and see if it makes sense. Again, this is in vertex form, so we can check the vertex first. We can see the vertex of this blue one is at 2, 1 right here, and that's what we see here. X minus 2 represents 2, and then 1 here. And then we have a negative in front of that function. That means it's a concave down parabola. When that a value is negative, it's concave down. So it matches. Everything works out. Through the transformation, we create a function that we see matches the equation we have here in vertex form. Hi there. Let's look at this problem here. Here we have a graph of function f of x, a parabola, and we are told that the a value is 1. It says write the equation in vertex form. So we're going to create an equation for this. And since a is 1, we don't have to worry about creating an equation by checking another point in it. We know it's just going to be a basic parabola with a equals 1. Therefore, all we need is the vertex. The vertex is at 4, 2. So to write that in vertex form then is this, x minus 4 squared plus 2. Remember that when we have a positive x value for the vertex, it is written as a negative here. And now you can see that clearly the connection between that, which we learned about vertex form parabolas way back when, and now with transformations. Imagine you began with a parabola that sits at 0, 0, with the vertex at 0, 0, and then you had to create this one. Well, you would move it over 4 units and up 2. And that's what we see here. Over 4 units, up 2. Vertex form and transformations are connected. Alright, now we're trying to create another parabola, g of x, and it's done through a series of transformations to f of x. So we're going to show those changes on the graph here. To create g of x, f of x is dilated vertically by a scale factor of 2. So vertical dilation means you're multiplying the entire function, and it means you're affecting y values. The scale factor is 2. That means each y value will double. This y value at the vertex is 2. So the new vertex y value will be 4. This y value here is 3. So the new y value for this one will be 6. Let's take a look at that graph. There it is. So that doubled, this doubled, every point doubles, and the parabola is stretched vertically. Next, this is followed by a reflection over the y-axis. So here's the y-axis. This parabola will reflect over the y-axis. So it'll end up being over here. The vertex was at 4, 2, now it is at negative 4. Sorry, at 4, 4, now it is at negative 4, 4. Finally, this is followed by a vertical translation down 5 units. Vertical translation, so again we're talking about moving up and down 5 units, so we go 1, 2, 3, 4, 5, right here, down 5 units, we end up being here. Okay, so here's the original parabola, here's the g of x parabola, 3 transformations. Now it says write an equation for g of x in terms of f of x. So we want an equation for this one in terms of f of x. That means the equation we write is going to be g of x equals something something done to f of x. And we know what was done, these 3 things. So there was a dilation vertically, and let's show all these things here. Here's that vertical dilation, scale factor 2. 2 times the entire function, 2 times f, because we are affecting y values. Then we reflect it over the y-axis. We can see that here. X values are made negative when you reflect over the y-axis, so x values are made negative here. And finally, we went down 5 units, so 5 is subtracted from the entire function because we're affecting y values. Now, it says write the equation of g of x in terms of x. So this is it written in terms of f of x, right? And now we're going to rewrite it where it doesn't have the f function in here anymore. It's just its own function for g of x. And the way to do that is to basically put this f function or apply these changes to the f function, and then we will have the g function, right? So let's multiply everything by 2. If we multiply everything here by 2, and that's what we see here, then there'll be a 2 in front, but this 2 is also multiplied. A lot of students forget that. Don't forget that. We're multiplying the entire function by 2, so this will become 4. And next we're going to substitute an x value of negative x in here, so that x will be replaced by negative x. And finally we will subtract 5 from the entire function. So from everything we have there, we will subtract 5. Let's take a look at what that looks like. It's right here. So here's the multiplier of 2 in front of this whole thing. Notice this 2 here became a 4. Like we talked about, the negative x was inserted right here. And then negative 5 subtracted from the entire thing. To simplify that further, we can rewrite it like this, where the 4 and the negative 5 are combined to make negative 1 here. All right, let's try this one. Here our goal is to write f base 2x in terms of f sub 1 of x. So the blue one, f1, is our first function, and the orange one is our second one. We're trying to change blue into orange. First thing I noticed when changing blue into orange is that the blue one should be vertically stretched for sure. Notice how much taller it gets. Well, how much taller is that? Let's take a look. Here's the minimum point here of negative 1 y value on the blue one. And that same location here is at negative 3. So that tells me this was stretched down times 3. Let's confirm that works with the maximum point right here, the local maximum. This point is at a y value of 0.5, 1/2. Multiply that by 3 and you get 1.5, and that matches what we have here. So we know our vertical dilation factor is 3. Everything becomes 3 times bigger, the y values. And then imagine the blue one now has the same shape as the orange one. It's all stretched out. It needs to move over to the left. How many units? Let's check from this intersection point here. 1, 2, 3 units over to become moved on top of the orange one. So to show both those transformations, we can show them here. We have the vertical dilation factor of 3, and then x plus 3 means it moves 3 units left. All right, just a few more. Here in this question, our goal was to change the f function into the g function. So we're going to compare them and see what's happening. Here is this x minus 5. I notice this x is now 4x, and I notice this negative 5 is negative 20. So both of those have been multiplied by 4. So we can show that the transformation there, to get g of x, we take the f function and we multiply by 4. That's a vertical dilation by scale factor 4. Let's show how that works. So we do 4 times f of x, 4 times this entire function right here, then multiply through and we get this, which matches what we have here. Great, let's look at b. In b, I see 2x and I see 6x. So first thought is, well, we multiply this by 3, right? But if we multiply this by 3, the 5 will also be multiplied by 3, and that won't give us that. So can we just affect x values rather than affecting the whole function? We can just affect x values. So here's how we're going to do it. We can put 3x into the f function. So that means this x is replaced by 3x. And when you do that, you have 2 times 3x, because that has been replaced with 3x. And that becomes 6x. And the 5 is unaffected, so we made the changes only to x, and we can see that the only x changes here. All right, last one. What do you see happening here? Here I see this negative 2x becomes positive, and this negative 5 becomes positive. Both become positive. That means the entire function can be multiplied by negative 1. So that is a reflection over the x-axis when we're making all y values negative. That, to show that there, we multiply the entire function by negative, and then it becomes what we see here. All right, great. Just one last thing. We didn't talk about what this transformation was. This is a horizontal dilation by scale factor of, well, the scale factor is 1 over 3, right? Because when we do horizontal dilations, remember, the effect on the graph is the reciprocal of what we see here. So we see a 3, therefore the effect on the graph is 1/3. Okay, let's look at this one. Here our goal is to take f of x, change it into g of x, but to do that using 2 different approaches. Use 2 transformations to change it into this, and then use 2 different transformations to change this into this. And this problem is all about seeing that there's multiple ways to get the same end result. There are different transformations that can take us to the same place. So let's look at one way. I see 3x here, and it becomes negative 3x. So why don't we replace this x with a negative x? That will then make this negative 3x. So that's taking care of this. And now this negative 8 needs to change into a 3, which means we have to add 11. So check it out. Negative x is inserted here, and then we add 11 to this whole function. Negative 8 plus 11 gives us 3. So let's show that work here. So negative 3 goes in here. Sorry, negative x goes in here, and then we add 11, and that results in the function we see. All right, so that's 2 transformations that get us to here. Let's look at what's another pair of transformations that can bring us to the same end result. So how could you do that? Well, I'm looking at it, and again, I see 3x and negative 3x. So the other way, I mean, we could insert negative x like we did, but the other way to do that is to, well, why don't we make the whole function negative? Because that will make this negative 3x as well. But if we make the whole function negative, then this negative 8 will turn positive. So imagine now you have positive 8, but you need it to be 3. What are you going to do to it? Well, you're going to subtract 5, right? We make the whole function negative, and then we subtract 5. Let's look at that here. So this 3x minus 8, the whole function is made negative, and then we subtract 5 from there. So we get negative 3x, and then this combines to become this, which works out. So you can see 2 different paths, 2 different pairs of transformations get us to the same place. Important to know. All right, we're cruising. Let's do another one. What's the next one? What do we got for you here? Ah, yes, I love this problem. Here we have a function f of x. It is a square root function. And we are going to apply some transformations to it and make sure we apply them just right to create the new function. First thing is we are vertically stretching it by a factor of 2. Vertical stretch means affecting the whole function, affecting y values, so we just put a scale factor of 2. So 2 times that root of x. Next, it is horizontally stretched by a factor of 5. So now we're doing horizontal. That means affecting x values. That means we're going to put a 5 in here, right? Wrong-o! No. Remember, horizontally, when it says scale factor of 5, we know it will have the opposite, the reciprocal in there. So actually, we have a 1/5 put in there. That will mean it stretches 5 times wider, but the number that goes in the function is 1 over 5. Okay, next. It is translated 21 units to the right. So that is affecting x values. So that means we just write minus 21 here, right? Wrong-o! We do not. We put x minus 21 in parentheses. Remember, when we're making changes to x, we replace the x with the new thing, and the new thing in this case is x minus 21. So we keep the parentheses there to show we have inputted that into the function. That is very different than if we didn't have the parentheses. That can be multiplied a little further to get this. All right, there's that function. Let's, hey, is that all? Perfect, you did it. You are now a master of transformations. Please study some more. You will be ready for our assessment. Can't wait to see you there later.